Welcome, everyone, and thank you for being here today. I'm excited to introduce our topic, internal landforming processes, focusing on Earth movements and tectonic forces. In this presentation, we'll explore how the Earth's crust is shaped by powerful internal forces that operate beneath the surface. We'll look at both lateral and vertical movements, their causes, and the fascinating landforms they create. We'll also delve into the theories behind these processes and examine mechanisms like folding and faulting that produce some of Earth's most dramatic features. So, let's get started. Horizontal Earth movements are essentially lateral forces that make rocks move sideways rather than up or down. These movements lead to different types of crustal deformation, which shape much of our planet's surface. There are three main categories based on how the forces act and the direction they push or pull. First, we have stretching, which happens when tensional forces pull rocks apart. Imagine pulling on a rubber band. This creates strain within the rocks as they elongate in opposite directions. Next, there's shortening, caused by compressional forces. Think of pushing two blocks of material together. This pushes the rocks inward, causing them to shorten and often buckle, forming folds or other structures. The third category is shear or tear movements. These occur when horizontal forces act in the same or opposite directions at different rates, causing rocks to slip past each other horizontally. This movement is critical in forming features like fault lines. All of these horizontal movements are responsible for some of Earth's most iconic features: fault lines, mountain ranges, and rift valleys. The specific deformation that occurs depends on factors like the direction, strength, and duration of forces, as well as the properties of the rocks involved. Understanding these processes helps us see how Earth's surface is constantly reshaped over time. Tensional forces happen when parts of the Earth's crust are pulled apart, causing the rocks to stretch. This stretching creates a lot of interesting geological features. For example, we see the formation of normal faults, where blocks of crust drop downward relative to their neighbors. This process can also lead to the development of rift valleys, which form when large sections of crust sink between parallel faults. Another feature we often observe is horst and graben structures. These are blocks of crust that are uplifted or downfaulted, creating a sort of blocky landscape. Tensional forces can also cause the crust to thin, and this thinning can allow magma from beneath the surface to rise up. Over time, if the tension continues, it can even result in the complete separation of crustal blocks, leading to the formation of new ocean basins. We see these processes most clearly at divergent plate boundaries, where plates are moving away from each other. A prime example is the East African Rift Valley, where the African continent is slowly being pulled apart. This slide illustrates how rocks respond to being pulled apart by forming normal faults and grabens, and it highlights the dynamic nature of Earth's crust as it responds to these tensional forces. It's a fundamental part of understanding how new geological features and ocean basins are created over Earth's history. Now let's talk about compressional forces and how they influence the Earth's surface. When sections of the Earth's crust are pushed toward each other, the rocks respond by shortening, buckling, and deforming. This process leads to some of the most striking landforms we see on Earth. For example, reverse faults occur when one block of crust is pushed up and over an adjacent block, creating dramatic vertical displacement. We also see the development of fold mountains, which form as layers of rock are compressed and bent into complex folds. These forces can also cause thrust faults, where older rocks are pushed over younger rocks, often creating impressive structural features. Another key effect is crustal thickening, which is a major factor in mountain building. The intense pressure can even lead to metamorphism, transforming rocks chemically and physically due to the extreme conditions. Most of these signals of compressional forces are found at convergent plate boundaries, places where tectonic plates collide. A prime example is the Himalayan mountain range, which was formed by the collision of the Indian and Eurasian plates. This entire process highlights how powerful compressional forces are in shaping our planet's landscape, reinforcing the overall theme of tectonic forces driving geological change. Let's talk about shearing forces and how they cause lateral displacement in the Earth's crust. Shearing or tearing forces happen when sections of the crust slide past each other horizontally. This can occur when they move in the same direction, but at different speeds, or in opposite directions altogether. Now, these forces are responsible for creating some pretty distinctive geological features. When shearing occurs, the top layers of rock often move more than the lower layers, or neighboring blocks might move in opposite directions. This results in horizontal displacement along fault lines. Think of it as the crust getting shifted sideways. One of the most common features we see from shearing forces is a transform fault. These are places where two tectonic plates slide past each other horizontally. A well-known example is the San Andreas Fault in California. Shearing can produce a variety of landscape features, like offset streams, linear valleys, and even sag ponds. And it's important to note that shearing can also lead to earthquakes. When friction along these faults temporarily halts movement, stress builds up until it's suddenly released, causing seismic activity. Shearing forces are especially prominent at transform plate boundaries. These boundaries are sometimes called conservative boundaries because, at these locations, crustal material isn't created or destroyed, it's just shifted around. That's why we see frequent earthquakes along these faults, as stress continually accumulates and gets released. So, in the bigger picture, shearing forces play a key role in shaping our planet's surface and driving seismic activity at these boundaries. Now, let's look at vertical Earth movements, which happen along the radius of the Earth, moving from the interior toward the surface or the other way around. These movements are quite important in shaping the Earth's surface features. First, we have up-warping and down-warping. When crustal rocks are pushed upwards, that's up-warping, often caused by compressional forces. Conversely, when rocks are pulled downwards, that's down-warping. These processes can lead to the formation of domes and basins, which are significant landforms in geology. Next, vertical displacement due to faulting occurs when the middle block between faults either subsides or uplifts. This displacement is typically driven by compressional or tensional forces and results in features like horsts. Those are the uplifted blocks, and grabens, which are the depressed blocks. Finally, there's vertical displacement with tilting. Sometimes, the land that is either uplifted or sunk can also tilt. This happens when the forces involved are of unequal strength, causing one side of a block to rise or fall more than the other. These tilting movements can create interesting and complex landforms. All these types of vertical movements are interconnected and contribute to the dynamic nature of Earth's surface, aligning with our overall theme of understanding Earth's geological processes. Let's explore the causes of Earth movements, starting with magma movement. Magma from the upper mantle can move upward and invade the Earth's crust, which can cause the crustal rocks to shift either vertically or horizontally. When large amounts of magma escape during volcanic activity, it leaves behind cavities or voids. These voids can result in the subsidence or sinking of the rocks above. Next, we have gravitative pressure. As these magmatic cavities form, the rocks above tend to move inward to fill the gaps. This inward movement creates pressure, which can deform the surrounding rocks. Essentially, this process is a gravitational adjustment, leading to vertical movements like subsidence. Moving on to convectional currents, these are circulating flows of molten rock within the mantle. The currents move from deep inside the mantle towards the surface, then horizontally across it, and finally back inward vertically. These currents generate forces that drive the movement of tectonic plates, which is fundamental to the theory of plate tectonics. Finally, there's isostatic adjustment. Think of the Earth's crust as being in a state of balance or equilibrium called isostasy. When the weight on the crust changes, for example, due to erosion or sediment deposition, vertical movements occur to restore this balance. It's similar to how objects float in water, adjusting their position based on their density. All these mechanisms work together to continuously reshape the Earth's surface. The way different types of crustal rocks respond to these forces ultimately determines the specific landforms we see in various regions. Understanding these processes helps us grasp the dynamic nature of our planet. Now, let's explore the concepts of continental drift and plate tectonics. In 1912, Alfred Wegener proposed a groundbreaking idea that all the continents we see today were once joined together in a supercontinent called Pangaea. Imagine Pangaea as a massive landmass surrounded by a vast ocean called Panthalassa. Wegener suggested that over time, Pangaea broke apart, leading to the continents drifting to their current positions. He identified two major landmasses that formed from this breakup, Laurasia in the north and Gondwanaland in the south, separated by the Tethys Ocean. Laurasia eventually split into regions like North America and Eurasia, while Gondwanaland fragmented into Africa, Australia, South America, Antarctica, and India. Now, what evidence supports this idea? Well, the continents bordering the Atlantic Ocean fit together like pieces of a puzzle. Paleoclimatic data shows that southern landmasses had climates consistent with being connected in the past. Major coal deposits are found beyond the tropics, which makes sense if these areas were once connected in warmer climates. Similar geological structures found across oceans also suggest these continents were once joined. Additionally, paleomagnetic studies, those are studies of ancient magnetic fields recorded in rocks, indicate that the continents share a common origin. And there's a great illustration showing Pangaea and its subsequent breakup, which really visualizes this process. Building on Wegener's ideas, the plate tectonics theory offers a more detailed explanation. It states that Earth's surface isn't static, but made up of large, rigid plates that are constantly moving. These movements are driven by convection currents in the mantle, the layer beneath the Earth's crust. When these plates interact at their boundaries, we see the formation of mountains, earthquakes, and volcanic activity. These are the geological features we observe and study. Finally, the major tectonic plates of the world are like enormous puzzle pieces fitting together to form the Earth's surface. Understanding these plates helps us grasp the dynamic nature of our planet and the processes shaping its surface over millions of years. Let's take a closer look at plate boundaries and their effects. First, we have divergent boundaries, which occur where plates move away from each other. This happens because of rising convection currents in the mantle. As hot magma rises, it pushes the crust apart, creating new material. You can see examples like the Mid-Atlantic Ridge, the East African Rift Valley, and the Red Sea. These areas are characterized by features such as rift valleys, volcanic activity, seafloor spreading, and the formation of new ocean basins. Next, we have convergent boundaries. These are places where plates move toward each other, leading to collisions. The specific features depend on the types of plates involved, whether oceanic meets continental, oceanic meets oceanic, or continental meets continental. For example, the Himalayan mountains formed where India collides with Eurasia. The Andes are created by oceanic Nazca Plate subducting beneath South America, and Japan sits above complex plate interactions in the Pacific region. These boundaries often produce mountain ranges, deep ocean trenches, volcanic arcs, and earthquakes. Then there are transform boundaries. These are locations where plates slide past each other horizontally. The movement occurs along fracture zones called transform faults. It's important to note that at these boundaries, material isn't created or destroyed, it's just offset. Famous examples include the San Andreas Fault in California and the Alpine Fault in New Zealand. Features here include fault lines, earthquakes, offset streams, and linear valleys. All of these interactions at different boundary types combine to shape our dynamic Earth system. They explain why we see earthquakes, volcanoes, mountain ranges, and ocean trenches. Understanding these boundaries helps geologists predict hazards and better interpret Earth's history. So, in essence, the movement and interaction of plates at these boundaries are fundamental to understanding the Earth's ever-changing surface. Folding and faulting are fundamental processes that shape the architecture of Earth's crust. Today, I want to focus on folding, which involves the bending of rocks due to crustal distortion. These bends can be upward or downward, and they mainly occur because of compressional forces. Think of tectonic plate movements pushing against each other. Let's look at some key parts of a fold. An anticline is a layer of rock that bends upward, forming an arch-like structure. Conversely, a syncline bends downward, creating a trough. The highest point of an anticline is called the crest, while the lowest point of a syncline is known as the trough. The axis is an imaginary line drawn vertically through the center of the fold, helping us understand the symmetry. The limbs are the rock layers on either side of this axis. Now, folds come in different types. Simple symmetrical folds have limbs dipping evenly away from the crest, creating balanced structures. Asymmetrical folds, on the other hand, have one limb steeper than the other, indicating uneven forces. Overfolds occur when an anticline is pushed over the limb of the next fold, creating a more complex structure. For recumbent folds, the entire fold is pushed to a horizontal position, almost flattened out. Nap or overthrust folds involve one limb being pushed forward over another, often producing dramatic geological features. The diagram here shows the various parts of a fold, helping us visualize these concepts better. In real-world settings, such as near St. Gothard-de-Lejeune in Canada, we see synclinal folds in bedrock, illustrating these principles in action. Overthrust folds, in particular, demonstrate how rocks can be pushed over great distances through tectonic forces. The type of fold that forms depends on several factors. Temperature plays a role. Higher temperatures make rocks more plastic and easier to bend. The amount of pressure applied and the type of sedimentary rocks involved also influence the fold's development. These folded structures are not just fascinating, they are responsible for many of Earth's mountain ranges. Additionally, they play a crucial role in trapping oil and gas deposits in specific geological settings, making them important for resource exploration. Understanding folding helps us grasp the dynamic processes shaping our planet and how geological